forget yet again. Okay, we are recording. Good. All right, so let's talk about what we're going to talk about. Tests of significance of proportions. So we're still dealing with proportions. Proportions deal with categorical variables. When we're dealing with categorical variables, we're dealing with proportions. When we're dealing with quantitative variables, we're dealing with means. So we did confidence intervals for proportions. Now we're going to do tests of significance for proportions. So what it means, really a lot of what it means is that when we go to use, excuse me, the central limit theorem, we're going to end up using this formula, either using pi or p hat, for calculating our standard deviations. And we're going to end up using this formula, n times pi greater than or equal to 10, and n times 1 minus pi greater than or equal to 10 for testing our conditions. So when we're dealing with categorical variables, these are two of the big differences between that and means. And I think I sent out yesterday again the little notes from Olivia Weiss, which also has my notes on it. And use that. I mean, it's going to help you remember which one to do. All right, so when we're talking about tests of significance, a lot of what we're going to talking about in this chapter is different terminology, is different notation, and a very fixed structure to follow when we're doing a significance test. So, pay attention to the terminology. It's going to be important. Here are some of the things we're going to learn about. We're going to learn about statistical significance. We're going to learn about tests of significance. That's the title of the chapter. We're going to learn about something called the null hypothesis and something called an alternative hypothesis. And we're going to have one-sided and two-sided of those. We're going to have a thing called a test statistic. And what will probably come up most frequently in your after stats life is this thing called a p-value. We're going to learn what a p-value is. And then we'll learn about significance levels and test decisions. Again, you're going to see a lot of similarities between this and confidence intervals, but because really they're all going to be based on the normal model. I mean, really, when we're talking about a lot of this stuff, we're always kind of going back to the normal model. And really, we're going back to the empirical rule is a lot of what we're doing. So, okay, this is an awkward sentence here, but it'll express kind of the difference between confidence interval and test of significance. So when we're trying to find a confidence interval, that is chapter 16, topic 16, we're trying to find two values between which we are confident that our population parameter lies. So we calculate a confidence interval using our p hat. We get two endpoints, and we are a certain percent confident that our population parameter lies between those 2 points. That's a confidence interval. But a significance test, we're actually starting with a hypothesis for the population parameter. So, and we're going to decide whether or not we can reject the hypothesis or whether we can not reject the hypothesis. We'll have an example here in a minute, but I just want you to notice, I'm not saying we are never going to accept the hypothesis. It's always a hypothesis. It can always be possibly wrong, but we can get enough evidence to reject it and say, nope, that hypothesis is no good. Or we can get enough evidence to say, I can't reject it. I'm not sure if it's right, but I can't say that it's wrong. There's a difference between saying that something is right and saying that it is not wrong. Because if you're just saying it's not wrong, there's still, or it's probably not wrong. You can say there's a probability that it might be right. Okay, so here are our objectives, same things we just talked about, but we're going to actually, the problems that we're going to work through are going to deal with almost all of these objectives, but we're going to talk about a null and alternative hypotheses. We're going to check conditions for whether a one proportion z-test is valid. This is going to have to do with our n times pi and our n times 1 minus pi, the same things that we've been doing. We're going to calculate something called a test statistic and a p-value. And then we're going to make a decision and summarize a conclusion. Yeah, these three things right here, these are all kind of like, how do we follow the structure of a test of significance? And there are several problems that you should do for practice, not a lot. So I got what, 1, 2, 3, 4, 5, 6, 7 problems. If you're doing that over a 3-week period, that's like, what's that? 7 problems over 3 weeks. That's like 3 problems a week. Is that right? I don't know, something like that. I just did that wrong. Less than that. It's less than 3 problems a week. So certainly manageable. Who knows anything about baseball? A couple people know something about baseball. You know how many innings are in a game, right? You know what an inning is? People who don't know anything about baseball, do you know what an inning is?
I think there are 9 innings.
There are 9 innings, yes. Yes, there are 9 innings, yeah. Well, we'll get to that when we get to that. I don't want to go into a lot of baseball stuff right now. Okay. All right, so let's have a little kind of discussion here. So I'm looking at number 2. We're going to consider a cola taste test. Okay. And we have 3 cups. We have 2 Coke and 1 Pepsi. So I call on somebody to take a test. I want to see whether they can tell the difference between which one's Pepsi and which one's Coke. And they taste 60 different times. So they taste all 3 of them 60 different times. And they are able to identify the Pepsi 21 times out of the 60. Are you convinced that they were really just guessing or that they really knew their stuff? 21 times out of 60. So let's think about this here for a second. So they're guessing, or they know the difference. Okay, how many people, based on this, getting it right 21 times out of 60, how many people are convinced that they know the difference? They can really tell the difference. Like 0 are convinced, huh? So how many people think that the subject might just be guessing? So we have opinions on this. Okay, and I would tend to agree with you, because if it's 1 out of 3, right? I mean, 1 Pepsi is 1 out of 3. I mean, that's a third. If I'm guessing, I mean, a third of 60 is 20, right? So they could just guess, get 1 extra one right, and be, you know, maybe a 21 out of 60. So how many out of 60 would a person have to get for you to be convinced that they weren't just guessing, that they really knew what they were doing? So I'm just going to get some numbers here. So Emma, what do you think? How many would they have to get right for you to be convinced that they weren't guessing?
Probably like 40.
40. Emma says 40. How about you, Brooklyn? What do you think?
I feel like 55.
55. Well, you're tough, man. 55 out of 60. Nikki, what do you think? Wait, it's not Nikki, is it? No. Who is it? I can't tell who's who in the room. I got Karina and I got who else there?
Alondra?
Alondra, okay, but your mouse is covering up everything. I can't tell who I even have. Or, oh, how many do you think, Alondra?
I'm gonna say half, like 30, 35. Probably.
Oh, really? Oh, you're easy. Okay, 30 to 35. Okay, Karina, what do you think?
I'll say 45.
You say 45. Okay, Alexi, what do you think? How many?
Maybe 50.
50. Again, you're pretty tough, huh? Sylvia, what do you think?
45.
45. Caitlin,
I would also say like 55.
55. My God, you guys are really hard. Okay, Reina,
I would say like probably about 45.
45. Okay, Juliana.
I agree with Caitlin and Brooklyn. I think 55.
Boy, you guys are really brutal. Okay, Megan,
I think 45.
45. Interesting. We're going to come back to this one. Abby,
I'm gonna say about 45.
okay. Alexis,
Maybe like 32.
32. Oh, no, there we go. Right, there's an odd number. Huh? Okay, Isa,
34.
34, another odd number. Okay, Brooklyn, I won't call on you twice, even though you're showing up here twice. Okay, all right. So we'll come back to that one when we're doing a problem on that. So if a subject identifies the Pepsi correctly in 40% of the sample trials, would you be more impressed if it were a sample of 200 trials or a sample of 20 trials? So a trial is tasting all 3 cups. Okay, that's a trial. And they get it right. They get the Pepsi right 40% of the time. Are you more impressed if they do that in 200 trials or 20 trials? And why? So I'll take a volunteer on this. Okay, Alexis, go for it.
I think I'd be more impressed if it was 20 trials they got 40% right instead of 200 trials, because like if you're tasting something like 200 times, you think you'd know what it is, versus if you're taking it like 20 times, I feel like that's like not as much. So I think that would be more impressive.
Okay, because 200 times you have more practice tasting. That's an interesting thought. Anybody want to argue for 20? Wait, you said 20 times because 200 more practice. You said 20 times would be more impressive. And anybody want to argue the other side that 200 times is more impressive?
Can I just add on what Lexi said?
Yeah, please go for it.
Oh, if you do it 20, like if you guess 40% correctly for 20 times, you get almost half, because I checked and it's like 8 of the trials you got correctly. So that's
Right.
almost half compared to 200, which means you only got
Should be 80.
Yeah, so I think it's better for, like, Lexi's logic is kind of like better though, but I think 20 is like more impressive.
Okay. Nobody's going to argue for 200? Well, I'm going to argue for 200. I'm going to argue for 200 because 200, because first of all, we know that there it's 1 out of 3 chance if you're guessing, right? That's a 33% chance of guessing it, correct? Right. So if I was to draw my diagram of all these samples here, the 33% is going to be right there in the middle, because if I just guess, I'm going to get it right 1 out of 3 times on average. Does that make sense, everybody? Yeah. Okay. So 40% is over here. Well, larger the sample size, smaller the standard deviation, right? this is my sample size versus that, I think that if I only did it for 20 trials, I would have a wider model, right? There'd be more likelihood than if I did it 200 times, my standard deviation is going to be much narrower. This 40% is going to be farther away from the mean. Am I making sense there? What I just said? Yes? Okay. Larger sample size, smaller standard deviation. All right. Let's collect a little data here. This is great. So this is a professor, two friends went into their professor, lied, and they said that they missed the test because they had a flat tire. Okay, now I want to, on a different subject here, are you aware that in college, most of the professors, if you miss an exam, will give you a 0. Are you aware of this? This is very important to be aware of because there's a lot of professors, they don't care if you got in a car accident, they don't care if you have COVID-19, they don't care, you know, whether you're getting your wisdom teeth out, doesn't matter. If you miss a test, you get a 0, no makeup, that's all there is to it. I know, isn't that terrible? I think that's awful. I think that's awful, but that's what they do. Mr. Oriana, is that your experience in college?
Not nowadays. I think a lot more professors have been a little more accommodating with the COVID-19 stuff.
Oh, well, that's good to
I think
hear.
it-
That's good to hear. With the but is it just because of the COVID-19 or is it in general?
I think in general too. I know of a story of a friend of mine who got into a car accident, walked himself to the class and showed like his nearly broken arm to the professor, and was like, "I can't take the test." And then the professor relented after that. But I mean, in
Okay.
my experience, I've always been accommodating.
All right, well
Generally.
then, listen to him, don't listen to me. No, check with your professor first, okay? Make sure you know what's going on there because you don't want to have that kind of problem. I don't know what my brother's policy is. I should ask my brother. My brother's probably one of the mean ones. My brother can be a real jerk. He really can be a real jerk sometimes. You know, we had Passover. I'm digressing. We had Passover the other night, Zoom Passover. So the whole family's, you know, people from the Bay Area, people from the East Coast, people from, you know, Davis, you know, they're all gathering together on Zoom to have Passover. My brother, he didn't show up. He's such a pill, I swear. He can be such a pill. Okay, I changed the subject. All right. So they lie and they tell the professor that they had a flat tire. And so he sends him into a room to take a makeup exam. The first question is worth 5 points and it's really easy. The second question is, which tire? Ooh, that's a good one, huh? That's a good one. So if you were caught in that situation, which tire would you say? Okay, so think about it for a minute. So Emma, which tire would you say?
I'd probably say right front.
You would say right front. Okay, Brooklyn, what would you say?
I was gonna say the right back.
You would say the right back. That's interesting. You're the first person that said a rear tire. Alondra, what would you say?
Right front.
Right front. Okay, Karina, what would you say?
I was gonna say right front also.
You say right front? I missed it. Yes, okay. Okay, Alexi, which would you say?
Maybe right rear.
Right rear, okay. Sylvia,
Right front.
right front, interesting. Nobody's on the left at all. Caitlin,
Right front.
wow. Okay, Juliana,
Left back.
left rear, okay. All right, Megan,
Left front.
left front. So we got a couple lefts here. Okay, Abby,
Left front.
left front. Oh, left is catching up. Reina,
I would say right front.
right front. Alexis,
I'd say left front.
okay. Isa,
Right front.
right front. Okay, interesting. Oh, we'll come back to that one too. I probably would say right front myself. Okay. So guess what? Kissing couples. Back to kissing couples. This is great. All right. We're going to learn all of these objectives in this example here. Okay. So let's get started. I emailed this out to you. I'm going to, come on, you know how to do this, Glenn. There we go. Do a page this way. There we go. Okay. We're going to read through the problem here together, but I emailed this out to you. There's 6 steps for a formal test of significance. Everybody got this? Yes? Okay. We were talking earlier, we're going to learn the steps for a formal test of significance. I am not going to make you memorize it. All right. But if you're ever reading about a test of significance, these are the steps that you have to go through. And we're going to do that with this problem here. So refreshing ourselves on the problem, we used the central limit theorem to determine the probability of obtaining a sample proportion as extreme as 0.645. So that was our p hat, 0.645. And we assumed at the time when we first did this problem that the actual population proportion was 0.50. That would have been our pi. That's what we were assuming, okay? P hat, our sample, pi, the population proportion. We had we had 124 couples. So that was our n equals 124. And then we had very strong evidence against the hypothesis that our pi is 0.50. Okay, now we're going to learn how do we do that in a formal test kind of a way. So let's click down here a little bit and see if I can make this work. So let's drag that down to there. Good. Okay. So step 1, give a description of the parameter, being sure to identify the type of number, whether it's a mean or a proportion, the variable, and the population. So this is we're going to write something here that identifies what are we trying to do with this test of significance. So if I was to do that on this problem here, I would say the parameter I am, let me think, how would I say this? I am indicate the parameter of interest. The parameter of interest is the proportion of couples who lean their heads to the right when kissing. Yeah, I think that's what I would write. How does that sound to you? That sound pretty good? And let's see what Beth says. I can't remember what Beth says. The parameter of interest in this study is pi equals the population proportion of all kissing couples. Well, I did pretty good. I just didn't put in pi, but oh, it says use what symbol you will use to represent it. The proportion of couples, pi. There we go. State 1, that's step 1. That's you have to write out what it is you're looking for. All right, let's take a look at step 2. Okay. I am going to state competing claims about the parameter of interest. So the first claim is called the null hypothesis. And that states that the parameter of interest is equal to a specific value. Now, frequently, it's a statement of no effect or no difference. So in the kissing study, the null hypothesis is that no difference between right and left. Now, I'm writing the null hypothesis before I do any research. This is kind of just like my statement that I'm going to do research about. Okay, so I'm going to say that the null hypothesis, which we write H sub 0, that hypothesis is that pi, the population parameter, is equal to 0.50. This was our original assumption. We were originally saying, my hypothesis is that makes no difference whether that half the people are going to turn to the right, half the people are going to turn to the left. That is my null hypothesis. Does that make sense? Okay, now we call it the null hypothesis. I used to think we called it the null hypothesis because it's H sub 0. And 0 is frequently referred to as null, like nothing there, right? But the null hypothesis, a better way to think about it, is the null hypothesis is what we are trying to nullify. We're going to take steps to figure out whether we can reject the null hypothesis, right? We want to nullify the null hypothesis. And maybe we can, and maybe we can't. So in this case, the null hypothesis, H sub 0, is pi is equal to 50%, 0.50. Are we okay with that? Are we okay? All right. So what we've done here really is we have taken what we wrote in words and we have just written it in mathematical symbols. So instead of in words, we've written it in mathematical symbols. Okay, still in step 2, we then have to, since we have the null hypothesis, we need to put forward an alternative hypothesis. Right? We're gonna compare the two. The alternative hypothesis only takes one of 3 forms. Okay, we're not going to say, oh no, I think it's 0.645, or no, I think it's 0.642. We're not saying that. All we are saying with the alternative hypothesis is that the parameter pi is less than the hypothesized value, is greater than the hypothesized value, or does not equal the hypothesized value. Those are the only 3 choices. So the null hypothesis, H sub 0, is always pi equals something, in this case, 0.50. My alternative hypothesis, and in this case, I kind of suspected that, like I kind of think, well, more people are right-handed, so more people are likely to turn to the right. So I suspect that pi is greater than 0.50. That's my suspicion. That is my alternative hypothesis. Don't get confused on the alternative hypothesis. The alternative hypothesis is simply saying that no, it's really greater than, or it's less than, or it's simply not equal to my my null hypothesis. Have I said that enough times? Yes, I've said that enough times. Okay, I'm sure we'll end up saying it more times. Okay, so the researchers suspected that more than half of all kissing couples lean to the right. So using symbols, it's right like that. Hypothesis sub A, so the alternative hypothesis is that pi is actually greater than 0.5. Okay, any questions? Nope, we're still doing okay? Okay, that was step 2. So we did step 1. We did step 1 and we did step 2. Now we're going to go to step 3. What a great idea. So step 3 says, specify the behavior of the sampling distribution under the null hypothesis. Okay, so there's a couple things we need to do for this. First, we need to check to see, can we use the central limit theorem? Okay, so there's 2 conditions we have to satisfy as to whether we can use the central limit theorem. Alexi, can you tell me one of those 2 conditions?
I guess one of those 3 conditions could possibly be. Wait, what was the question again?
So
Sorry,
I need
on
to
a call.
check. I need to check to see whether the central limit theorem, whether I can use the central limit theorem. And there's 2 things I need to check to determine whether I can use the central limit theorem.
Okay. It could be maybe randomness or the sample size and normality of it. Of the
That's
sample
exactly right.
distribution.
Randomness is one of them. And you have to be clear on that. Somewhere in the problem, it has to state, or somewhere in the actual experiment or the actual study, it has to state that the sample was drawn randomly. The other thing involves a formula. Raina, do you know what the formula is?
I have no clue.
No, we just talked about it a minute ago. Do you have that sheet there that how to determine whether we can use the central limit theorem? You know what sheet I'm talking about? Not sure? Hang on a second here. Unit 4. Maybe it was unit 3. I can't believe I can't find this. I couldn't find this the other day either. And then so, oh, maybe it was in topic 13. I can't believe this. I mean, on here, let's do it this way here. Lessons. Okay, Olivia. Topic 13, 15, formulas from Olivia Weiss. I sent this out. You guys should have this, okay? This is giving you every single formula you're going to need to do all these central limit problems. And what it says here, if I'm using the central limit theorem, CLT, for categorical variables, I have to have n times pi greater than or equal to 10, n times 1 minus pi greater than or equal to 10. If I don't have that, I can't use the central limit theorem, and I'm just going to stop the problem. So in this particular case, if I know my n is 124, so 124 times pi has to be greater than or equal to 10. Now, pay attention, okay? When we were doing confidence intervals, we were using n times p hat because we had a p hat. We're doing tests of significance. We use n times pi. So we go 124 times 0.50. That's definitely greater than 10. And we do 124 times 1 minus 0.50, which is really 0.50, the same thing. And that is greater than or equal to 10. So it is random. And we use the formula that involves the sample size. It's big enough. Am I making sense here? Yes, classroom, thumbs up. Good, okay, everybody's good. All right. So I'm going to draw a picture. That's what I'm going to do now. I'm going to draw my picture. So I know, because I'm using the central limit theorem, that it's going to be unimodal and symmetric. Doesn't it look kind of like a little Pac-Man ghost? Kind of like a Pac-Man ghost. Y'all play Pac-Man, right? Everybody's played Pac-Man. Does anybody not play Pac-Man? Everybody's played Pac-Man. Yeah, when I was living in Detroit, I went through a period where I was having a lot of struggle, and at lunchtime from where I was working, I would go to the arcade. They had arcades then, you know, and I would play Pac-Man, and I actually got like what is it, tendonitis in my elbow? Is that what it's called? You know, I mean, my elbow was like totally shot. I could hardly move my arm from playing Pac-Man so hard. Anyways, I can draw the diagram. What's going to be the center? Magic ball. What's going to be the center of this diagram? Juliana, what do you think? What's going to be the center?
Is this centered like the mean?
Center is the mean. As I said, it's right in the middle there. Yeah. Was somebody making fun of you over there? Who's making fun of you?
My mother.
Tell her to stop. Don't make fun of her. She's a nice kid. Right, go ahead. Go ahead. Is she laughing? I hope she's not mad at me for saying that. No, okay, that's good. Okay, what's gonna be in the middle?
Is it 124? Like, is it? No, that's for the central limit theorem. Hold on.
That's okay.
Do we put the sample size?
No. It's a good guess. All right, let's give somebody else a chance to listen carefully. You really need to know this. All right, so oh, Imani's not here. Emma, what am I going to put there in the middle?
I was really hoping you wouldn't call on me this weekend.
You really hope I wouldn't call on you. Well, you know, magic bowl, I can't, you know, I mean, I wasn't doing it on purpose.
Yeah, it's at the mercy of the gods of probability.
I can give you a guess.
You say you're going to make a guess? Go ahead, make a guess. That's fine.
Is it 124?
No, but that's okay. That's what Juliana just said.
Oh.
No, come on, pay attention. Here we go. Okay, wait. Reina, do you know what I'm going to put in the middle? Yes? No? Reina, you with us here?
Oh, I thought you called on Karina. I was
No,
like,
no, I called you. I'm sorry. Okay.
I really want to say 124, but I feel like that's not it.
That's definitely not it because Juliana and Emma just said that.
Oh, I can't hear. My Wi-Fi's been going out, so I can't hear most of like what happened in the past.
Oh, that's not good. Okay. So you're not sure what I'm going to put in the center. Okay, listen up. Who knows? I'll take a volunteer. Okay, Caitlin, what do you think?
0.50.
That's exactly what I'm going to put here. I'm going to put 0.50. I am going to draw my picture. So remember, central limit theorem says, this is the great thing about the central limit theorem. I mean, the central limit theorem is awesome. If I know, the central limit theorem says, if I pass the qualifications, random and adequate sample size, I can determine the shape, the center, and the spread of the sampling distribution. I mean, this is like astounding. This is what lets us tell the probabilities. I know that the shape is going to be unimodal and symmetric. The center is going to be the center of the population. Now, I am drawing this assuming under my null hypothesis that H sub 0 pi is equal to 0.50. So that's what's going to go here, is going to be pi. Now, I just want to draw a distinction between this diagram and what we were doing for confidence intervals. When we were doing it for confidence intervals, we were starting from our sample. So we would use p hat as our center. But for tests of significance, we're starting from our null hypothesis. So we are using pi as our center. This is an important distinction, right? Confidence intervals uses p hat. Test of significance uses pi. I would just write that down so you make sure that you're clear on that. Confidence intervals are going to use p hat. Test of significance are going to use pi. So our center is going to be pi. So I've got my center right there. 1, 2, 3, -1, -2, -3. So back to the magic bowl. Somebody's got to tell me, how do I figure out my spread here? How do I figure out the spread? Sylvia, do you know how I figure out the spread?
So are you gonna have to figure out the z-score to determine? I mean,
No,
I'm
not
a little
z-scores, not yet.
okay. Is it the standard deviation of the population? No.
Yes,
Yeah.
yes. I need to figure out the standard deviation. So what is the formula for figuring out the standard deviation?
So it's I forgot the name, but it's like the square root symbol.
Square root,
Pi,
uh-huh,
parentheses 1 minus pi over n.
That's exactly right. This is going to get us my standard deviation. So let's call up a little calculator over here. Come on, calculator. There we go. Okay, so I have pi, which is 0.5. It's not the 0.645. It's the 0.5. 0.5 times 1 minus 0.5, which is also 0.5, divided by my sample size, which is the 124. And let's take the square root of that. And I find out my standard deviation is equal to, we'll call it 0.045. Oh, yes, Abby, you were right. I didn't see your chat there, but you were on target there, obviously. Good. All right. So I'm going to complete my diagram. So I'm going to go 0.5 plus 0.045 plus 0.045 plus 0.045, and I get, this is 0.545, 0.59, 0.635, and then I'm going to go the other way, 0.5 minus 0.045 minus 0.045 minus 0.045, and I get 0.455, 0.41, and 0.365. So I've got my diagram here. Pretty good? Okay, everybody okay with this? Any questions? All right. So let's where did I go? So here is, okay, got that. So I got my diagram. Let's move this way up here. I don't want that. Here's that. Let's move this down to here. Okay, so I did step 3. Okay, and you can see step 3 says randomness, and then the sample size, normality of the sampling distribution. That's our n pi greater than or equal to 10. Okay. So what I'm going to do next is I'm going to calculate a test statistic. Now, this is a funny kind of a word, but the test statistic is the z-score of my sample. And I even wrote that in here on step number 4. The test statistic is a measure of the discrepancy between our observed statistic, which was 0.645, that was our p hat, and the hypothesized parameter. So I'm trying to find out how far away is what I observed from the parameter that I'm trying to find out, from my null hypothesis. So I'm going to find the z-score for 0.645. So we know that z equals x minus x bar over s. So z equals 0.645 minus our middle from our diagram, which was pi 0.50, divided by, well, this right here is what I just calculated here for my standard deviation. So I know that that's 0.045. So I find out that I go 0.645 minus 0.5, divide that by 0.045, and I get a z-score of 3.22. This is my test statistic. This is how far away I am from the mean of my sampling distribution. And if I kind of go back to my picture, well, I can see that 0.645 is 0.645 is like way over here. 0.645. This was my p hat. My p hat is more than 3 standard deviations away from my null hypothesis. Right. Well, I mean, do you think I'm going to end up rejecting my null hypothesis or not? I think I'm going to end up rejecting this thing. I think my sample is so far away from my null hypothesis that I'm thinking, nah, I mean, it was a nice thing to hypothesize, but I really can't, I have to reject it. I'm going to have to reject it. And on Thursday, we're going to calculate the p-value that allows us to reject it. Is that okay if we do that on Thursday? No objections to doing that on Thursday? All right, I'm gonna remind this group. Run through the tape. All right, run through the tape. We don't have that much longer to go. So let's and this is like the best part. All right, you're out a little bit early. Have a nice day. It's nice outside. We'll see you later. Good to see you.
Thank you.
And make sure to give yourselves breaks. Highly important. Before you go, could you make sure to clean up just